Let's say, for the sake of argument, you are Alice and you're in Wonderland, and there's a magical carousel. You, being the daredevil that you are, sit on the carousel, and it goes around once. And contrary to common sense, you're not very started. Now the carousel goes around once more, and boom, you're back where you started. What if this insane magical carousel had mathematical footing and is the foundation of quantum mechanics? Wouldn't that be insane? But here's where things get wicked. Let's ignore quantum. What if I told you these weird mathematical oddities had grounds in classical mechanics? Wouldn't that be wild? Electromagnetic waves are transverse waves, which means they jump up and down while moving forward. Now, these waves can be rotated, like so. This is called polarization. Now, for the sake of simplicity, we can ignore the magnetic part of the EM wave and just focus on the electric part. Let's say the wave is propagating along the Z axis and it's oscillating along the Y axis. This can be expressed trigonometrically like this. Here's a fun fact for you. This can be represented using complex. Basically, complex numbers can be expressed using Euler form and trigonometric form. You basically ignore the imaginary part and just pay attention to the real part. We pretend that E is complex. It's not, but we can pretend it is. Then we can just express it using the Euler form. We can do the same thing for oscillation along the x-axis. Now, by using a combination of these two vectors, we can express any E wave. Know that we need to worry about the z-axis because z is the direction of propagation. Here, we can add these two vectors because EM waves are superimposable. Now we can ignore the z component and create a new vector. We call this the Jones vector. This represents the polarization of the wave. By modifying its parameters, we can represent any polarization. Any given polarized wave can be expressed as sum of horizontally and vertically polarized waves, h and v. We can ignore the phase and amplitude because this doesn't affect the polarization. Now we can construct some basic EM waves with these two polarizations. First is the diagonal wave. We rotate the vertically polarized wave by 45 degrees clockwise. The next is the anti-diagonal wave, which we get when we rotate the vertically polarized wave by 135 degrees clockwise. Next, we have the left circularly polarized wave, which occurs when we have a 90-degree phase shift between the vertical and the horizontal components. And right shift polarized wave, which is when there's a 90-degree phase shift between the horizontal and vertical components. Boom, you have four fundamental polarizations. Polarization can be changed by two magical relics. One is the polarizer, and the other is the mysterious wave plate. The birefringent crystal is an intriguing relic that can create a phase difference between the vertical and the horizontal component. We all know that we can transform a vector using a matrix. That is, a matrix is nothing but a linear transformation. So we can represent this intriguing relic as a matrix. The matrix that phase shifts the vertical component by 90 degrees is called a quarter wave plate. If we pass in a diagonally polarized light wave into a quarter wave plate, it becomes a left circularly polarized wave. The math works out like this. And we pass in a left polarized light wave into a wave plate, it becomes antidiagonal. And repeating this again gives us a right circularly polarized wave. And again, if we pass this wave into a crystal, we get a diagonally polarized light wave again. We can represent this as a circle. Iota represents a 90-degree phase shift. We can change this to represent any arbitrary angle phase shift like this. So we can shift the given wave into any one of the given components of the circle by multiplying it with this transformation matrix. We know that only the phase of the vertical polarization is affected by the wavelet. So if we pass in a horizontal wave, it will remain unaffected. However, if we rotate the crystal by 45 degrees in the anti-clockwise direction, it's equivalent to rotating a light wave in 45 degrees in the clockwise direction. Now the wave has a vertical component, so it can be affected by our crystal. We can represent this rotated wavelet like this. So the horizontal wave becomes L, which then becomes V, which then becomes R when we apply the transformations over and over again. Now we can combine the two transformations we have like this into a sort of a sphere. We can derive the relations between H, A, V, and D. So now we have a fully completed sphere. We call this the Poincare sphere. We can represent the three relations like this. By generalizing these matrices, we can reach any point on the Poincare sphere. Let's pause here to summarize some stuff. The polarization can be represented by a Jones vector, and the polarization can be transformed by a wavelet, which can be represented by a matrix. Now, we have a set of configurations of polarizations, which can be represented on a Poincare sphere. We can go to any point on the sphere by transforming it using the three matrices we have derived. Any matrix that transforms a 3D real vector without scaling it is called an O3 matrix. Note that both rotations and reflections belong to the O3 group. If the determinant of the matrix is positive and equal to 1, then it's a rotation. Otherwise, it's a reflection. We set the determinant equal to 1 because there is no scaling involved. If the matrix does not scale a vector and the determinant is positive 1, then it belongs to a group called SO3 matrix. The Jones vector we have is complex, so we cannot transform it using a regular O2 matrix, which only works for real numbers. Matrices that transform complex numbers without scaling them belong to the U2 matrices. Now, we know that the overall phase difference does not affect the polarization and therefore the Jones vector. So we have a number of matrices that do the same thing but with different overall phase difference. To remove this discrepancy, we set an additional requirement with the determinant of the matrix be set to positive 1. This will give this will yield a special set of matrices called the SU2 matrices. Let's revisit the Poincare sphere. Here, the horizontal and the vertical configurations are 180 degrees apart, but in the physical space, they are 90 degrees apart. So one full rotation in the physical space implies two full rotations in the Poincare sphere. So therefore, this Jones vector that I've been yapping about is nothing but a spinor. Spinors have two iconic characteristics. First, they do not care about the overall phase difference, and second, they do not care about the overall scaling. Notice how polarization is just classical physics. There's no quantum magic involved. Spinors power up in classical physics quite naturally. Isn't that wicked? For the next video, maybe we'll explore the role of spinors in quantum mechanics. That'll be fun. So consider subscribing. See ya.
See ya.